to speak on a topic I really love, activated random walks. I'm going to motivate the topic by talking about a model that preceded activated random walks, which is the Abelian Sandpile. And what we'll see is that this sandpile, although it has some beautiful features, it also has some non-universality. And once that non-universality was discovered, the search was on for a more universal model. And so I'll talk about the kind of design space of abelian networks which generalize the Abelian sandpile. And we'll look within that space for a universal model, and activated random walk will be the kind of natural candidate that falls out. Okay, but what are these things models of? So yesterday we had this picture of three phases of the Ising model, right? So, we had the subcritical where the interface between plus and minus was a straight line, and we had the critical where it was an SLE, and we had the supercritical where it was noise. And the thing about this critical phase is it's very delicate, right? You have to set the temperature of your magnet to this exact critical temperature if you want to observe this SLE interface. And that's a little bit of a puzzle because in nature we observe power laws, fractals, and long-range correlations in many situations. But when we go to make a mathematical model, like in this Ising example, it's only at critical values of the parameters that we actually see these features of power laws and long-range correlations. So these models were invented to kind of address the question of why do we see so many power laws in nature? And why do we see long-range correlations in nature? So these questions were asked by Bach, Tang, and Weissenfeld in 1987. And they came up with a purported answer to these questions, which they called self-organized criticality. Okay, and their idea, although it still hasn't been realized in its full potential, inspired quite a lot of work by mathematicians and physicists. And the idea was that some systems have a kind of regulating mechanism where even if you they have a dynamics where even if you start them far away from the critical value, the dynamics tends to drive them toward the critical value. So in the example of the magnet, it's a bit artificial, but imagine that you hook up your magnet, you put it inside a bigger system which also contains a thermostat. Okay? And the thermostat is wired so that it turns on every time it detects magnetic field, and it turns off when it stops detecting a magnetic field. So then when your magnet gets too hot, it will demagnetize, and then your thermostat will turn off, and the magnet will cool down, and then so this kind of system you could see might tend to keep the magnet at criticality. Okay, so that's a kind of artificial setup, but there are natural systems that do this kind of thing. And the example that Bach-Tang and Wiesenfeld proposed is a pile of sand. And the parameter, instead of the temperature, you should think of the slope of the pile. So imagine dropping sand on top of this pile. And when a sand grain falls on the pile, it might just stay where it landed, or it might kind of trickle down the pile a little bit and dislodge some other sand grains and create a cascade or avalanche of sand falling down the pile. And what you find is that there's a critical slope where you see power law distributions in terms of if I drop one grain of sand on the pile and ask how many sand grains are dislodged as a result, that will follow a power law. And that only happens at the critical slope. But what happens is if you have a flat sand pile, so you're less than the critical slope, then you have very small avalanches, exponential tails. And so your pile over time will tend to get steeper. And if you had a supercritical sand pile, then even a small disturbance of dropping one or a few sand grains will create a massive avalanche, which would tend to flatten the pile out. So you have a driving dynamics, which it takes flat piles toward the critical slope, and it takes steep piles also toward the critical slope. Okay, so this is kind of the motivating physical picture. And there are lots of physical systems that in principle behave like this. There are earthquakes, there are forest fires where you have trees growing slowly and occasionally burning down portions of the forest. So there the parameter is like the density of trees. There's financial markets where the parameter is like how much leverage or debt there is in the market. When you have more leverage, things are more unstable. When a bank fails, it can cause its counterparties to fail. And you see these things like in weather events, right? Like rainfall is something where water evaporates sort of at a slow, steady rate, but then it's released. The tension is released in sudden bursts, storms, and rainfall. So all these kind of systems where like tension is accumulating slowly and then is released in sudden bursts are kind of the type of things that we're trying to model. And so to turn this into math, what Bach-Tang Wiesenfeld proposed, and then it was investigated a few years later by Dar. So the Abelian sandpile on say finite or infinite graph G. Okay. Let's make it locally connected. So we'll say that a sandpile is just an integer valued function on the vertices. You can think of positive values as counting number of sand grains at a vertex. So S of V. So if S of V is positive, think of S of V sand grains. I'll just call them chips for short at vertex V. And we'll sometimes be interested in sandpiles where S of V can be negative. So there you can think of a hole which can be filled by chips. So it's a hole of depth. Absolute S of V. Okay, and how will these chips move around? So we want to capture the idea that if you have too many chips in the same place, they destabilize each other and spread around. So we say that if S of V is bigger than the degree of V, then V can topple. And toppling means sending one chip to each of your neighbors. By sending one chip to each neighbor. So it's useful to write down topplings in terms of the graph Laplacian. So this takes a function on vertices to another function. Whose value at vertex I is the sum over edges incident to I of the difference of values across that edge. And so we can express a toppling by adding the Laplacian of a delta function to S. So if I take the function delta I, which is 1 at I and 0 elsewhere, its Laplacian is 1 if j is adjacent to I, degree I if j equals I, and 0 otherwise, right? So So toppling vertex I, right, will transform the sandpile S to the sandpile minus degree I, S plus the Gaussian of delta I. Okay, and these topplings are most interesting when you have a sequence of them. So we're going to start with our sandpile S, and we'll topple some vertex x1, and we'll get S plus delta x1. And then we'll topple another vertex x2. And so on. Now, one thing I haven't specified yet is what order to do these topplings in. So what we're about to see is that there's a sense in which the order doesn't matter. So suppose I have a sequence of vertices x1 through xm. I'll call it legal for the sandpile. Let's say S0 is our starting sandpile. So it's going to be legal if we're actually able to perform these topplings in this order. So Si minus 1 of xi should always have enough chips greater than dxi for all I. Okay, where this Si minus 1 is the sandpile I got from toppling the first I minus 1 vertices in the sequence. So I get Si from Si minus 1 by adding delta delta xi. Okay, so this is just a way of saying that whenever I try to topple the next vertex in the sequence, I always have enough chips to do that. Is this too low to see? Yeah. Now, sometimes it might happen that I can't topple anything, and then I have to stop. So the kind of dual of being legal is being stabilizing. So I'll say that X is stabilizing for my sandpile S0 if Sm is pointwise smaller than a degree.
where is this sequence of vertices here in this definition?
So
because you take the end.
yeah, so this
okay.
x
Okay,
is
okay.
x1 through xm. Maybe I shouldn't call this x, I'll call this y or something.
Yeah, okay. And this is the nth track.
Right. So okay, so let me write down a quick example and then we'll see in what sense order doesn't matter. So so here's my graph with 4 vertices and 5 edges. And here's my, so I'll draw my sand pile just by writing numbers on the vertices. So there are 2 chips here, and 4 chips here, and 0 chips here, and there's a hole of depth 1 over here. And so you see in this example there are 2 vertices where there are at least as many chips as the degree, right? So I could topple either the upper left or the upper right. So if I topple the upper left, it's supposed to send 1 chip to each neighbor. And so I'll end up with 0 chips at the upper left. And this neighbor gains 1, this neighbor gains 1, and this stays the same. And now I can topple the upper right, and the upper right has 3 neighbors, namely all 3 of the other vertices, so they each gain 1. And now it loses 3, the others gain 1, so 1, 2, and 0. And this sand pile here is stable. Because every vertex has fewer chips than its degree. Okay, and in this example, it's very easy to see that order wouldn't matter. So I could have, say this is x1 and this is x2. So here I toppled x1 and then x2, but I could topple x2 first. And then topple x1, and I get to the same final stable sand pile. So we want to show this happens in general. Before I show that, though, maybe I should give an example of a sand pile that doesn't stabilize. So if okay, so consider this sand pile. So there's only 1 unstable vertex up here. If I topple it, it will give 1 to each of its neighbors. And now this one up here is able to topple, and if I topple that, now the lower left is able to topple, and if I topple the lower left, then oh, did I add a chip somewhere? What happened? So lower left is 0. Thanks, Carla. Okay, and now I have 2 vertices able to topple, and let's see, if I topple to the lower right, then I'll get back where I started. So this sandpile over here, we saw that it stabilizes, but this one doesn't stabilize. So one thing to notice here is that whether or not you stabilize depends on more than just the total number of chips. So in both cases, the total number of chips was 5 in these 2 sandpiles, but this one stabilized and this one did. Okay, so I want to say formally what it means that order doesn't matter. So this lemma is often called the Abelian property. So fix the initial sandpile S, and suppose there exists a stabilizing sequence. S. Actually, I'll call it Y. That's how it is in my notes. Then so any legal sequence x1 through xl is a permutation of a subsequence of Y. That would be the main point, and what follows is one, that there exists a legal and stabilizing sequence. and any two such are permutations of each other. Any two legal and stabilizing. Sequences for S are permutations of each other. Okay, so like in this example, there were two legal stabilizing sequences, x1, comma x2, and x2, comma x1. And in this example, there were none. So what's getting us off the ground is this supposition at the beginning that there exists a stabilizing sequence.
What do you mean, second point?
Part two.
Yeah.
So we've assumed only that there exists a stabilizing sequence, but part two says there exists a sequence that is both legal and stabilizing. Those are the sequences we're really interested in, because those are kind of what's allowed in our dynamics.
So you can be stabilizing without being legal.
You could be stabilizing without being legal, right? So it turns out it's useful to allow that extra flexibility of, you could think of being stabilizing without being legal as, I'm just forcing a vertex to topple even though it doesn't have enough chips. And so it will create a hole there. And sometimes that's a useful thing to do. More questions? So I usually skip the proof, but it's a mini course, and the proof is, something that's good to see at least once. And so it's just an induction on the length. So induct on M, the length of the stabilizing sequence. So given a legal sequence X, well, the first vertex we're supposed to topple already has enough chips since X is legal. Okay, but Y was stabilizing. So at the end, if we topple all the sequences in Y, all the vertices in Y, then we better be stable. So in particular at x1, there's strictly less than a degree x1 chips. Okay, and well, the only way you can reduce the number of chips by adding the Laplacian of something is if you actually toppled the vertex x1. Because if you do topplings anywhere else, that can only increase the number of chips at x1. So the only way to have this strict inequality is that one of these y's has to equal x1. So now we'll remove yi and x1 and induct. So now the shorter sequence x2 through xm, this is legal for S after we've coupled x1, and the sequence of y's where we remove yi is stabilizing. Okay, so now we're done by induction. So that's all it is. You just say that the first vertex in the legal sequence has to appear somewhere in the stabilizing sequence. Remove them both and induct. Okay, and so that's part one. And then for part two, you can take any maximal legal sequence, meaning of maximal length, has to be stabilizing. Because if not, if say, after doing the legal sequence, you had some vertex that still had enough chips, let's call it Z, had some vertex Z that had enough chips to topple, then you could append it to get a longer legal sequence. Okay, how do we know there is a legal sequence of maximal length? It's by part one, because the stabilizing sequence is an upper bound on the length of all the legal sequences, since any legal sequence is a permutation of a subsequence of a stabilizing thing. So that's how we know there exists a legal sequence. It's also stabilizing. And then part three is just, apply part one in both directions. If you have two sequences and they're both legal and stabilizing, then each one is a permutation of a subsequence of the other one, so they're equal up to permutation. Okay, so the upshot of this abelian property is that we're free to ignore the fine details of exactly which topplings are happening in which order, and just think about given a sandpile, it determines if either it doesn't stabilize or it determines a unique stabilization. So the odometer of sandpile S is the function that records how many times each site toppled. So U of X is the number of occurrences of X in any legal stabilizing sequence for S. Since they're all equal up to permutation, this function is well defined. And the stabilization is the sandpile S plus Laplacian of U. So if you want to think about, given S, how would you find the odometer U? Right. Once you've found the odometer, you could find the stabilization just by this formula. So there's a kind of corollary of this lemma, which goes by the name least action principle, which says that in a certain sense, this U is the smallest function that it possibly could be, namely the infimum of, say, W of x, such that the infimum is over all non-negative integer valued functions on the vertices, such that S plus Laplacian of W is less than degree minus 1. So, right, this inequality somehow tells you that W, it gives you a recipe for stabilizing the sandpile S. And among all recipes for stabilizing, you take the most efficient one, the one that uses the least, pointwise least number of couplings. On Thursday, I'll show you some pictures of stabilized sandpiles. So one thing that makes sandpiles very interesting is the integrality here. So if you think of this as it's an integer program, and even for very simple initial conditions like a large pile of chips at the origin in ZD, the stabilization has a lot of beautiful fractal structure. And a common thing to do when you have an integer program is to look at its relaxation, where you drop the integrality constraint. If you replace this n here by non-negative reals, you get a model called the divisible sandpile. Replaces n by non-negative reals. So that's where you replace your discrete chips by by mass that can be subdivided arbitrarily, and all of this fractal structure disappears in that setting. Okay, I didn't get to any probability yet, but it's coming. Thanks.
Thank you. Any questions?
So is there a continuum version of that?
Continuum. Is there a continuum version? So, okay. I mean, one way to think about continuum is replacing the discrete chips by mass. But you're asking about spatially? Yeah. So there's something called Healy-Shaw flow, which is it's like the process of like injecting fluid into. So you have like two parallel plates, and you have a kind of droplet of fluid that's trapped between them, and then you inject more fluid, and you see how does the shape of this droplet expand. That's a continuum analog.
You know the convergence of the discrete to the...
Okay, good. So what's interesting about this integrality condition is, like, unlike many discretizations, it doesn't totally disappear in the limit. Like, you might think, for example, if you start with a very large sandpile in Z2, where all the chips are initially at the origin, and then you stabilize it. Okay, so you've got this, this determines an odometer, which is a function on Z2, an integer valued function. You might not think it's very important that it's integer valued, since it's so large, that maybe the integrality just doesn't really matter in the limit. But it turns out to still matter, and so there is a scaling limit, but it isn't the Healy-Shaw flow. It's a scaling limit which kind of remembers that it used to live on this, like, infinitesimal square lattice. It's a lattice-dependent limit. So if you replace Z2 by a different lattice, then the limit changes. Yeah.
The divisible sandpile converge to
The divisible sandpile does converge to the Healy-Shaw flow, yes.
So if no more questions, let's thank Lionel again.